heat, the water vapor separates from the lithium bromide and it goes to state 3, which is the condenser. Now in the condenser, the water vapor converts to high pressure water. Then it goes to state 4, where you have the water is diverted to an orifice or an expansion valve, which basically converts the high pressure water to low pressure water. Then it goes to the evaporator, where the low pressure water evaporates by taking the heat from the surroundings, producing the cooling effect. Now, if this were connected to a chill water loop, which is serving a building or an industrial site or a campus system, basically you can get up 44, 46 degree chill water with the use of waste heat. Waste heat can also be converted to additional electricity through the most commonly you have steam turbines and organic Rankine cycles. In steam turbines, you have high pressure steam that rotates the turbine blade and that produces electricity. You have 1 megawatts to about 500 megawatts size range. It's a long working life and very high reliability system. Organic Rankine cycle, basically it uses organic fluids instead of steam. It uses the change of state of the organic fluid to drive the turbine. It has low waste heat. It requires low quality waste heat and can function very well on low temperature waste heat. It has very low maintenance as well. Now let's talk a little bit about the benefits of CHP. CHP operates at a very high efficiency. As a result of that, you have reduced emissions and reduced energy costs. It also enhances energy security and reliability. It increases energy choices and also enhances power quality. Let's talk a little bit about CHP and energy security. CHP can basically operate independently of the grid. Natural gas, which is the most commonly used fuel, provides reliable fuel throughout prolonged outages. CHP can power whole facilities, does not rely on wood poles, and CHP microgrids can power campuses, blocks, or neighborhoods. Actually, there was a recent law passed in September 2009, which HB 1831, which mandated all government facilities to examine the feasibility of CHP in their critical infrastructure. Now, to look at why CHP is efficient, basically you have very high efficient fuel utilization. The waste heat is captured for useful work. You don't have the transmission and distribution losses that is typically associated with the grid, and your efficiencies range between 70 to 90%. Now let's look at this imaginary building which requires 49 units of energy, 20 units for electricity and 29 units for heat. On the left-hand side is your conventional generation, which consists of power plant to produce electricity and an on-site boiler fuel. To supply the 49 units, you require 100 units of energy. On the right-hand side is the combined heat and power system, which supplies the same 49 units of energy required by the building by 57 units of on-site energy. The typical efficiencies for your conventional chiller, boiler, and separate heat and power is about 40 to 50% efficiency. And as we said before, combined heat and power basically has efficiencies in the 70 to 90% range. Let's look at the emission signature of CHP systems. On the left, you can see the emissions from CHP systems, and on the right is the emissions from the grid. On of importance to note, there is significant reductions in all the major greenhouse gases. If you look at it, it's almost 1,200 pounds of carbon dioxide per megawatt hour is what the grid emits. A comparable CHP system basically emits 600 pounds of carbon dioxide for each megawatt hour production. To summarize, typically you will receive 47% carbon dioxide reduction, 99% sulfur dioxide reduction, and a 93% NOx reduction. I think it is important here to mention the relationship between CHP and environmental revenue streams. Basically, environmental revenue streams rewards high efficiency and clean energy technologies. It provides a revenue through the sale of NOx and CO2 reductions. There are several programs in the country which either exist or in the developmental stage. You have the Regional Greenhouse Gas Initiative Program. It's basically a CO2 program. You have the Western Climate Initiative, which is also a CO2 program. You have the carbon dioxide offset programs in Oregon and Washington. You have the New Source Review Program, and you have the Renewable Portfolio Standard. Now, 12 states in the U.S. currently include CHP and waste heat recovery as eligible resources. Now, waste heat is basically has zero emissions. If we will get into a particular case study explaining that further. Now, let's look at the recent Texas projects and also some case studies of CHP installations. This one is the Thermal Energy Corporation, TECO, which actually serves all the chill water and steam needs at the Texas Medical Center in Houston. The existing TECO plant efficiency was about 40%. At that time, it had 16 megawatts of on-site generation. You had 80,000 tons of chilled water, and you had 750,000 pounds per hour steam packaged boilers. Now, with the installation of the new CHP plant, the efficiency shot up to 80%. It is basically some details of the plant. It is a 100 megawatt CHP plant. You have a 152,000 ton hours capable chill water storage tank. You have 540,000 pounds per hour of steam being recovered with the use of the heat recovery steam generator. And as a result of all this, you displaced the load and the duty on existing boilers, and thereby reducing emissions levels as well.